Welcome back, kiddos. Today's podcast is going to talk a little bit. We're going to talk a little bit about ionic equations, net ionic equations, and just some a little bit of review. So let's take a look at some review. Let's take a look at what are some assumptions. We've already done this, but let's look at it again. Reactions are spontaneous, which means that they occur right when the reactants miss. They automatically just react. Reactions are fast. The reaction must occur within a reasonable time. They are quantitative, which means we can use our stoichiometry, and we can also say that there's more than 99% completion of one reactant to be completely used up. We know that that one reactant is your limiting reactant. And reactions are stoichiometric, means that there is a simple whole number ratio of chemical amounts of reactants and products, and we use the coefficients of the balanced equation to set up a molar ratio, right? And the molar ratio goes from one substance to another. So let's take a look at net ionic equations. So a chemical reaction equation that includes only reacting entities, molecules, atoms, and/or ions, and omits any that do not change. This is what's really important. If they don't change, we kind of have to think about what's going on, what's changing, what doesn't changing. What if things do not change, we cancel them out. So let's take a look at the different steps. First step is write a complete balanced chemical equation. Make sure that it is balanced correctly and make sure that all of your compounds are written correctly. Dissociate all highly soluble ionic compounds and ionize all strong acids to show the complete ionic equation. Okay, so what the heck does that mean? A high solubility ionic compound is any compound that is aqueous. So for example, NaCl, because it's aqueous, we dissociate that. We ionize all strong acids. So if I have something like this, okay, it's aqueous, and because of the H here is an acid, we ionize that. And you know what that looks like. What ionize means is just break down into its ions, right? Plus Cl minus Aq. So basically we're dissociating, but we call it ionization because it's with an acid. Cancel identical entities that appear on both the reactant and the product side. So that's very important. You're canceling identical entities that are in the reactant and the product side. So if I have Cl minus in the reactant side and I see Cl minus, sorry, Aq, because they're exactly the same, one is on the reactant side and one's on the product side, they cancel out. And write the net ionic equation, reducing the coefficients if necessary. So once everything's canceled out, we write a new equation without those canceled entities, and we call that the net ionic equation. So let's practice. That's it. Let's do some practice. Write the net ionic equation for the reaction of aqueous barium chloride. So we are reacting aqueous barium chloride and aqueous sodium sulfate. We need to refer to our solubility table to see which of the products that results from that is the precipitate. So I'm going to write it down, and we know that it's a double replacement reaction. So the cations switch places, which is going to give us barium sulfate and sodium chloride. If we use our solubility table, this is not soluble. That is why there's an S there. So now what we're going to do is we're going to dissociate all soluble entities. Okay, so keeping in mind any of the subscripts. So let's take a look here. No subscript in barium, so it's one barium ion with a +2 charge. Notice there's a subscript here, and it's aqueous, so I'm dissociating both of them. There are two chloride ions that are aqueous. Going back to here, it's also aqueous. This time there's two sodium ions, so 2 Na+, and there's only one SO4 polyatomic ion, so only one SO4 2 minus. Cool. Take a look over here in our product side. This is what we decided was the not soluble entity, so it's solid. So because it's solid, we do not dissociate it. It stays as solid. And right here, because we balanced the equation, notice this coefficient here. That goes to the sodium and to the chloride ion. So when we dissociate, there's 2 sodium ions and there's 2 chloride ions because of the coefficient. All right? So step number 3, we are going to cancel out anything that is exactly the same on both sides. Well, let's take a look. Barium 2 plus on the reactant side, there's no barium 2 plus on the product side. There's barium sulfate, but there's no barium 2 plus, so that doesn't get canceled out. Let's take a look at the two chloride ions that are aqueous on the reactant side, and we notice there's exactly the same. So because they're exactly the same, we actually cancel these out. Okay? Because they're the same, they did not change. If something does not change, it doesn't go through a reaction. All right, let's see if we can find 2 sodium ions that are both each with a positive 1 charge. And we notice there's one exactly here. The coefficient is the same, the ion is the same, and the charge is the same. And so is the aqueous. So they cancel out. Okay, awesome. Now let's go ahead and look for SO4 2 minus. We'll notice that SO4 is here, but it's not 2 minus, so those do not cancel out. So then what we do is we go ahead and write out the equation again, keeping, not including all, do not include the entities that are canceled out. Okay? And we get something called the net ionic equation. Now these guys that are canceled out, they have a specific name. They are called spectator ions. So ions that are present but do not take part in a change, so they stay the same, they're called spectator ions. You have to keep that in mind. That is something that will show up on a test, spectator ions. They are the ones that do not partake in the equation. They do not change. They are the same. They are canceled out. We call those spectator ions. Okay, let's do another practice. Write the net ionic equation for the reaction of zinc metal. Okay, so obviously it's a metal, so it's solid. And aqueous copper 2 sulfate. Okay, and we're going to refer to our solubility table. So here's our zinc metal. Notice that there's a solid here. We have copper 2 sulfate, it's aqueous, right on. And then we have copper solid because it's a metal, and it's a single replacement reaction, right? So the metals change places. And then we have zinc sulfate that is aqueous. So let's dissociate what we can, and obviously not dissociate what we can't. All right, zinc solid stays the same because it's a piece of zinc that's solid. It doesn't break down, right? Because if you took a piece of zinc, it's a piece of zinc. So this guy is aqueous. We're going to break it down. There's no subscripts. Remember, this is a subscript, but it belongs to a polyatomic ion. It's not a subscript from a charge. So there's one Cu2 plus, and there's one SO4 2 minus. This exists in your periodic table in the polyatomic ion chart, so do not change it. Here's our copper solid, right? It doesn't change because it's a piece of copper solid. This guy is aqueous, so we're going to break it down to the zinc 2 plus, that's aqueous, and SO4 2 minus. Make sure you use your periodic table to look up the charge. All right, now we call that the complete ionic equation. Now let's go take a look and get rid of entities that are exactly the same on both sides. Well, here's zinc solid, and on this side, it's zinc ion. It's zinc 2 plus ion. They are not the same. We don't cancel them out. Here's copper 2 plus, and here's copper solid. They are not the same. We don't cancel them out. Here's SO4 sulfate ion, and here's the sulfate ion. Are they the same? Same, same, same. We cancel it out. What do we call those again? We call those spectator ions. So once we go through all of that, we rewrite it, because this is the net ionic equation. and it does not include spectator ions. Okay, no spectator ions here, and that's about it. So let's do another one. Write the net ionic equation for the reaction of hydrochloric acid, right? Don't forget it's aqueous if it's acid, and barium hydroxide. Okay, right on. Let's take a look. Now we have, this is a double replacement reaction. So what we're going to do is we're going to switch these guys. Okay, and when you switch those guys, you get barium chloride and water. Notice that water is a liquid. Okay, it is not aqueous. Water is a liquid. So let's go ahead and take a look at dissociating only things that we need to. So here we have, this is aqueous. Remember the coefficient is like the distributive property goes to both. So we have 2 hydrogen ions that are aqueous, 2 chloride ions that are aqueous, because all solids are aqueous, but we don't dissociate, we ionize. And that's just a word you need to know, that's all. Barium hydroxide is also aqueous. If you haven't noticed already, kiddos, this is a neutralization reaction. Here's your acid, here's your base. Anytime you have an acid base, it neutralizes. This is a type of salt. And obviously the second product is always water. Okay, it's a double replacement reaction, just happens to be a neutralization reaction. All right, anyways, back to business. There is, for barium hydroxide, there's 1 barium ion with a positive 2 charge. Here's a subscript telling you that there are 2 hydroxide ions with a negative 1 charge. Okay, moving on to, here's my arrow showing I'm moving on to the products. This is also aqueous. So I have 1 barium ion with a positive 2 charge. Here's a subscript, kiddos. 2 chloride ions with a negative, 2 chloride ions with a negative 1 charge. Liquid is not aqueous. I do not break it down, dissociate, nothing. Liquids do not dissociate. Okay, they do not. You know what else doesn't dissociate? Gases. If I had chlorine gas, that is not aqueous. That's a gas. They do not break down into 2 chloride ions. Okay, our next one is to go ahead and cancel things that are exactly the same. 2 hydrogen ions on this side. Here's hydrogen, not ions, is just water because it's liquid and we didn't break it down. So that stays. 2 chloride ions here. On this side, here's 2 chloride ions. They cancel out because they're exactly the same. Moving on to barium. Barium has a charge of +2 and it's aqueous. Look, here's a +2 charge. That's barium. Exactly the same. They cancel out. Here's hydroxide. Cool. You would see that it's the hydroxide is here because water is the same as HOH. However, this is liquid. This is aqueous, so they do not cancel out. How many spectator ions do I have? I have 2. I have chloride ions and barium ions. Those are my 2 spectator ions. So moving on, here's my net ionic equation. So when this happens, here's the chemistry. All this stuff, all these spectator ions, they're just there to hang out. They're not actually taking part in the chemical reaction. Remember, chemical reactions, there's a new substance being formed. Okay, that's it, kiddos. We talked about limiting and excess. Remember, you just have to know the definitions. A limiting reagent or a limiting reactant is the reactant that is all used up in a stoichiometric equation. All right, that's it.